Hi, this is Alex from devstories.eu. SunPy, Solar Data Analysis, Episode 11 of 12. Solar images are visually stunning, but sometimes the most critical information is just a single scalar flux value measured 1,000 times a second. When you track a solar flare's intensity over an entire week, a two-dimensional spatial matrix is simply the wrong tool for the job. You need 1D temporal data with TimeSeries. It is a common mistake to reach for the map object by default when starting with SunPy, but map is strictly for two-dimensional spatial data. When you are dealing with one-dimensional temporal data, like an X-ray light curve spanning several days across multiple wavelength channels, you use TimeSeries. It acts as the one-dimensional equivalent to map, designed specifically to handle time-indexed measurements while safely preserving observation metadata and physical units. Under the hood, a TimeSeries object relies on a pandas data frame to structure your timestamps and data columns. The problem with working directly in raw pandas is that standard data frames do not understand scientific units. TimeSeries wraps this data structure to ensure your physical units and instrument metadata remain firmly attached during operations. Consider loading an X-ray light curve from a GOES 15 satellite file. You pass the file path to the TimeSeries function, and it returns an object containing multiple observation channels as columns. You can inspect these columns by name, such as the short wavelength channel and long wavelength channel. Here is the key insight. Instead of extracting raw numerical arrays directly from the underlying data frame, you extract columns using the quantity method. You call quantity and pass it the specific column name you want. This method returns the data as an AstroPy quantity object. This means the raw numerical flux values are strictly bound to their physical units, like watts per square meter. Extracting data this way completely prevents silent unit conversion errors downstream in your mathematical calculations. Once you have your data loaded, you rarely need the entire observation file. You might only want to isolate the exact hour a solar flare peaked. You achieve this by truncating the time series. First, you define a time range object by providing a start time string and an end time string. You then pass this time range directly into the truncate method of your time series. This slices the underlying data frame and returns a brand new time series object. The data is cleanly cut down to your exact window of interest, and all the associated metadata survives the cut. Often, your analysis requires data that spans across multiple separate observation files. If your goal is to build a continuous week-long dataset, you load your second file into its own time series object. Then you simply call the concatenate method on the first time series, passing the second one as the argument. SunPy aligns the time indices and merges the data rows. As long as the instrument metadata from both files is compatible, you get back a single unified time series object ready for continuous analysis across the extended time frame. When processing temporal data, strictly binding your timestamps and numerical values to their physical units is what separates a reliable scientific analysis from a silent calculation failure. That's all for this one. Thanks for listening and keep building.